So here's an introductory note to the chemistry course. Chemistry is the study of matter and the properties of matter. Matter is anything that takes up space and has mass. So basically it's everything except for energy. We have pure substances and mixtures. So matter is divided into pure substances and mixtures. So is divided into. So you're either a pure substance or a mixture. If you're a pure substance, you're either an element or a compound. An element is made up of only one type of atom and cannot be broken down any further. So example of this: iron, sodium, copper, oxygen, hydrogen, carbon. Compounds, on the other hand, are made up of at least two atoms bonded together, and you can break them down into elements, but you require energy to do so. So compounds can be broken down into elements. So compounds can be broken down into elements, but it requires energy. We need some form of energy to do that. So if you're not a pure substance, then you're considered to be a mixture. And there's two types of mixtures. There's homogeneous mixtures and heterogeneous. Now homo means same and hetero means different. So when you have homogeneous mixtures, we call them solutions, and it looks like one substance. It's uniform, but it could be at least two substances where one is dissolved in the other, but at least two substances are involved. For an example, salt water. So you've got salt dissolved in water. Air. Air, we have a whole bunch of different gases like oxygen, nitrogen, argon. And heterogeneous. Brass too. That's copper and zinc. Heterogeneous mixtures, these can be identified because you see the different parts of them, and they can be easily separated. You can pick them apart or you can sieve them. Basically, trail mix, chocolate chip cookies, soil, salad dressing, all of these do not look uniform in appearance, so they are heterogeneous mixtures. So matter is either pure substance or a mixture, and we're really going to take a look at elements and compounds quite a bit in later solutions. So the periodic table identifies all of the known elements, and it's organized into columns called groups and rows called periods. There are 18 groups, and some of them are identified as families because they have similar properties. For example, group 1 is called the alkali metals, and these are the most reactive metals. Group 2 is called the alkaline earth metals, and these are almost as reactive as the alkali metals. Group 17 is called the halogens, and these are the most reactive nonmetals. Group 18 are the noble gases, and they don't react at all. So a family is a group of elements that behave in the same way. So the most commonly named ones are group 1, alkali metals, group 2, alkaline earth metals, group 17, column 17, the halogens, and then group 18, the noble gases. Quite often, the halogens react with the alkali metals to form salts. Okay, so where are these groups on the periodic table? It would help to have some pencil crayons here. So the alkali metals are those below hydrogen. The alkaline earth metals are beside the alkali metals. The halogens are over here to the right hand side, and then the noble gases are at the very far right. Hydrogen is on here because even though it's in column 1, group 1, it is not an alkali metal. You have to remember that. It's in group 1 because when it does form an ion, mostly it just shares electrons, but if it does form an ion, usually it's the 1+. Sometimes it's put above the halogens, group 17, because sometimes it can form a -1 ion. Okay, it's really important that you understand where the metalloids, metals, and nonmetals are on the periodic table. So the easiest thing to do is to do the metalloids first. Let's start with boron. Boron's a metalloid, then silicon, germanium, arsenic, antimony, tellurium, and polonium. So these are the metalloids. The nonmetals are all of the elements to the right of the metalloids, with the exception of hydrogen. Hydrogen is also a nonmetal, and that means all the other elements are metals. So there's way more metals on the periodic table than there are nonmetals and metalloids. Each element in the periodic table has its own unique number called the atomic number. This is, by definition, the number of protons found in the nucleus. Atoms are neutral, so it also means the same number of electrons. So protons and electrons are equal, and they're equal to the atomic number. The elements can also have a mass associated with them, and this is found underneath the atomic symbol on the periodic table that I give you. This is an average mass of all the isotopes for that element. If we round off the mass to the nearest whole number, we get the mass number. If we subtract the number of protons from the mass number, we get the number of neutrons. So for instance, if we look at hydrogen. So hydrogen has an atomic number of 1 and a mass of 1.01. So the atomic number is 1. So this is your atomic number, and this is the mass number. So round this to the nearest whole number, so 1, and that will equal the number of neutrons. So 1 minus 1 is 0. So hydrogen has no neutrons in its nucleus. Now let's do another example. Let's do nitrogen. Nitrogen has an atomic number of 7, and it has a mass of 14.01. So our mass number is the mass rounded to the nearest whole number, so 14, minus the atomic number. This up here is the atomic number. equals the number of neutrons. So 14 minus 7 is 7. So an atom has 7 neutrons in its nucleus. So pause this video and see if you can come up with the mass number, atomic number, and the number of neutrons for these 4 elements using your periodic table. So basically, if you take the middle number from the top number, you get the number on the bottom. So 19 minus 9 is 10 neutrons. 7 minus 3 is 4. 9 minus 4 is 5. So protons, neutrons, and electrons make up the parts of an atom. And so we call these parts the subatomic particles. So what I'd like you to do is copy this table into your notes. So protons are positively charged, and we have the symbol of a P with a plus charge as a superscript. So that's a P with a plus sign up top. Has a mass of 1 atomic mass unit. So that's atomic mass unit. And we find them in the nucleus. We also find the neutron in the nucleus. It's neutral, it has no charge. And because of that, we write 0 as a superscript for 0 charge on that particle. It's the same mass as a proton, 1 atomic mass units, and it's also found in the nucleus. And your nucleus is like a fortress. Those parts do not move in a chemical reaction. So this is a fortress. What moves are the electrons. The electrons are in energy rings or levels around the nucleus. So an electron is negatively charged. So we write an E with a superscript with a negative. And the mass is 1 over 1830 atomic mass units. So what that means is it is 1830 times lighter than a proton or a neutron. Or you could say we need 1830 electrons to equal 1 proton in terms of mass. And we find these on the rings around the nucleus. So this diagram just shows you that the mass between a neutron and a proton is equal. And here, 1 electron is a fraction, a very small fraction of the mass of a proton. So we need 1830 electrons to equal the mass of a proton. So the mass of 1 electron is 1 over 1830 atomic mass units. And then this diagram to the right shows you, here's the nucleus here in the middle, and it contains our neutrons and our protons. And then we have these energy levels, these rings around the outside. And you might remember this from grade 10. The first ring can only hold 2 electrons. The second ring can only hold 8, and the third ring can only hold 8 electrons. And basically, the number of elements on a row is equal to the number of electrons on a ring in a Bohr diagram or a Bohr-Rutherford diagram. Okay, this diagram shows you the difference between a Bohr diagram and a Bohr-Rutherford diagram. So this side is a Bohr, and this side is a Bohr-Rutherford. we can sometimes say chemistry is boring. Haha, boring. Okay, it's not. Okay, so we have a nucleus in both. We have energy levels on both, and we have places for electrons to go on both, and there's a limit to how many electrons can fit on a ring. And I'm using these diagrams to show you how I'd like you to do your Bohr diagrams or your Bohr-Rutherford diagrams, because it's going to help us figure out how many bonds an atom will make later, depending on how many unpaired electrons it has. So this is how we're going to draw them. So the valence shell is the outermost energy level, or the outermost ring, with electrons in it. These electrons are called valence electrons. Any other electrons between that ring and the nucleus are called inner electrons. So if this is my nucleus, here's my first energy level. Here's my second energy level. These dots are my electrons. You put one on each side first, then you start doubling up. So on my valence shell, this is the outermost shell, I have 5 valence electrons. I have 5 valence electrons in my valence shell. And then the 2 on the first ring are inner electrons. Okay, so cohort B and O, but not BO, I want you to open the Google Slides, and you're going to fill it in from here, because you can't fill it in easily on the Google Doc. Okay, so draw the Bohr-Rutherford diagrams for lithium and fluorine. Well, to recap, so we know we're doing Bohr-Rutherford, so we need protons and neutrons. So lithium had an atomic number of 3, so there's 3 protons, 3 electrons, and it had 4 neutrons. And we got this from the tables we just completed. So 3 protons, 4 neutrons, and that means we fill in three electrons. Fluorine, atomic number 9, so it has 9 protons, 9 electrons, and 10 neutrons. Again, we got that from our table we just did. So 9 P pluses, 10 neutrons, and now we fill in the 9 electrons. So 1, 2, 3, 4, 5, 6. You see I'm going clockwise before I start doubling up. 7, 8, 9. So we're finished. So these are our 2 Bohr-Rutherford diagrams. Now lithium is a metal. Fluorine is a non-metal. So these guys like to react. So what happens is, in a reaction, the metal wants to give up electrons, so it gives up an electron, and fluorine will take it. So we're going to form ions. But basically that's how reactions happen. One in case of metals and nonmetals coming together, the metal gives up its electrons and the nonmetal accepts them. All right, so now we're going to do Bohr diagrams for two elements. Bohr diagrams for beryllium and oxygen. So now, because we're just doing Bohr diagrams, we don't have to put the details in the middle. We just put the symbols in the middle. So we've got beryllium and oxygen. Now beryllium had an atomic number of 4, so it has 4 protons and 4 electrons. So we're going to fill in the first 2 on the first ring, and then the second ring gets 2 electrons, but you put 1 at the top and then 1 at the right. We fill clockwise. When we get back to the top, then we start doubling them up. So oxygen has 8 electrons because it has an atomic number of 8. So 1, 2, 3, 4, 5, 6. Now we start doubling up. 7, 8. So now we have the Bohr diagrams for 2 elements. Beryllium is a metal. Oxygen is a nonmetal. So what's going to happen if they react? Beryllium will donate both of its electrons to oxygen, and they will form a compound. When metals react and form ions, so an ion is an atom that has gained or lost electron. In this case, we're talking about losing. So when metals react and form ions, they lose electrons from the valence shell and become positive ions. So they become positive. The number in the charge of the ion will indicate the number of electrons lost. So on the left here, we have a regular sodium atom. This is just a sodium atom. It has 11 electrons. But it wants to lose this 1 electron because it's the only electron in its valence shell. And it either wants to be full or empty. When you're a metal, you want to be empty. So it's going to lose that electron. So instead of being sodium, it becomes a sodium ion. And it lost, so it's positive, and it lost 1 electron. So it's Na1+ or Na+1. It doesn't matter which way you write it. And you could, if you had a Bohr diagram like this, pre-made, you would either have an empty valence shell, or you would eliminate it altogether, like is shown here. But now the ion goes in the center of your diagram. So nonmetals also react and form ions, except this time they gain electrons and they become negatively charged. So they're the opposite of the metals. The number in the charge will indicate the number of electrons gained. So chlorine. Over here on the left, we have a chlorine atom with 17 electrons. It's got an atomic number of 17. So its valence shell is almost full. So it's going to gain 1 instead of losing 7. So now it is a chloride ion. When you have a nonmetal, we change the ending to IDE. So now we have a chloride ion, and you have the symbol. It gained electrons, so it's negative. It only gained 1, so it's 1 negative. You can write -1 or 1 negative. It's okay. So what I want you to do now is to draw the Bohr diagrams for the ions formed for lithium, beryllium, oxygen, and fluorine. And you can look back at your Bohr diagrams that you've already done to help you identify it, or use your periodic table. So pause this video and try them. So here we go. This is what your structures should look like. So these two are identical except for their charge, but their Bohr diagram looks very similar. And then the same for oxygen and fluorine. So this becomes oxide and fluoride. So they've got the same number of electrons, just their charges are different. So we call these, if you have the same number of electrons, we call you isoelectronic. Isoelectronic means the same number of electrons. And all of these are isoelectronic with a noble gas. This is the same configuration for the helium atom. It's got an atomic number of 2. And the neon atom. Running out of room. One, 2, 3, 4, 5, 6, 7, and 8. So basically, ions are always going to be isoelectronic with a noble gas. Okay, they're always going to be isoelectronic with a noble gas. They're either going to lose, like the metals, to become like a noble gas, or they're going to gain electrons, like the nonmetals, to become like a noble gas. So that's pretty much the review for parts of the periodic table and Bohr Rutherford diagrams.